All right, so we're going to move on to example 3 today. Remember from the notes that we talked about yesterday, so real quick, I'm going to rewrite it. We've got, this is our base exponential function. It's y equals ab to the x. So I'm going to write that down just to kind of talk about, to reference as we go here. And basically we want to think of this is your start value. This is your rate. And this is your time periods. So sometimes years, sometimes minutes. It all depends on what the problem's about. So those are the things we've got composing this up. So it says you got a large city, 4.6 million people in 2010, rate of 1.3% for the next 4 years. Okay. The first part, which is actually worked through here, says what exponential function models this population over that 4-year period. So we're going to put this equation together. We start with 4.6 million. Now you could write 4.6 million if you wanted to, or you can just write 4.6 and know that your population is measured in millions. Both are fine. Usually it's just nicer to call it 4.6. So that's going to be our start value. Our rate, it's going up by 1.3%. Now, 1.3%, you'll notice gets rewritten as 1.013. The rationale there is you want to write it as like 1 plus the rate. And the rate is 0.013 when you convert the percentage to a decimal. And the reason that you got to do this and the reason that you get it to this value is that now when you multiply this number, it's going to be an increase. If you just put in 0.013 and let's say you take that population of 4.6 and you multiply by 0.013, it gets really tiny. And it's population growth, not a decay. It shouldn't be getting smaller. So this number is what it gets added on every time. So to do this a little more efficiently is you multiply it by 1.013, and that goes ahead and adds this growth to the 4.6 already to give you what you want. So this is the value you're going to want to use when you're talking about these rates. So anything above 1 is going to cause it to grow or to get exponentially larger. And then the t is going to be your time. Now, they have the equation set up right here. They said population is equal to 4.6, which is your start value, times the 1.013, which is your growth factor. And the t is, you'll notice it's years since 2010. So because they said this started in 2010, so like if they ask you the population in 2015 or 2020, you have to say, oh, that's 5 or that's 10 years later, and that's the value you're going to use because it's your number of time periods that have passed. So we've got equation that looks good. Now it says the population continues at the same rate. Will the population be in 2040? So all we've got to do to figure this out, take our equation and evaluate it at the correct number. So from 2010 to 2040 would be 30 years. So we can evaluate this, and this will give us what we want. All right, so 6.777, so 6.8, roughly 6.8 million. And again, just remembering that your answer is in million people, and there we go. All right. Nothing too crazy. You could put this in the y equals. You go look up various values if you wanted to. So especially useful for questions that have multiple parts. If you type it in like this, you could then jump to the table and you could go look up any number you wanted. What do they have after 1 year? What do they have after 10 years and so on? And obviously you can hold it and you can jump down to 30 if you want to see the answer that we just had is boom right there. So again, nice easy way to look up multiple values using a table like that. All right, so we got a little try it problem here. It says, factory purchased a 3D printer in 2010. The value of the printer is modeled by this, where X is your number of years. Now you'll notice this would basically show that, okay, it was $30 to start with, and 0.93 is basically saying, all right, it's keeping 93% of its value. Or you could think of it as it's losing 7% of its value. So it's going to depreciate. It's going to lose value over time, like most things do. Very few things gain value over time, some collectibles and stuff. But other than that, most things lose value over time. So what's the value of the printer after 10 years? I'm going to go ahead and put it in the calculator, in the y equals, just so that I can look at various values if I want to. But if I type this in, I can see, okay, at year 0, I can see the initial cost, which is going to be 30. After 1 year, it's dropped a little bit. But I want to go 10 years, so we'll go ahead and jump down here. So at 10 years, it's worth $14.52 roughly. Okay. Does the printer lose more of its value in the first 10 years or the second 10 years? So if I look at 10 more years later, that's now down to $7. Okay, $7.03. So if you think about it, it went from $30 to $14 to $7. So much more is lost in the first 10 years because you're losing a percentage off of a bigger number. And as you're losing a percentage off a bigger number, basically this got cut in half and then this got roughly cut in half is about what happened there. But here you're losing $15, $16. Here you're only losing $7 or $8. So definitely the first 10 years. Okay. And that's going to be true for everything ever that has decay like this. If it's exponential decay, you lose more value in the first several years than you do in the later years because you're taking a percentage off a bigger number. All right, what else we got here? Growth and decay, we've already used these terms a few times, but growth is anytime you're increasing. So it's going to be 1 plus whatever the rate is. If it's increasing at a rate of 1.3% or 10% or whatever, you put that rate in. And if it's decreasing, like our last one was losing 7% of its value, you subtract that number. And so the concept is if the value in here is greater than 1, it's growth. And if the value in here is between 0 and 1, it's decay, which makes complete sense. You're either having over 100% or you're having under 100%, and that's going to cause increase or decrease. All right. So number 4 here says a car was purchased for $24,000. Here's the function that shows its value after X years after it was purchased. So does it represent growth or decay? You look right here, that number, which we call our B value is less than 1, and that implies decay. Okay. The rate of decay is 0.8, which means, I don't know why I put an E there, which means so this would be like 80%. That means it's keeping 80% of its value. It means it's losing 20%, which means it is losing 20% of its value each year. Okay. So it keeps 80%, loses 20%. Both mean the same thing. Graph function on a reasonable domain. Do the y-intercept and asymptote represent? When will it be about $5,000? Okay, so let's go ahead and jump to our calculator and put this in. 24 times 0.8 to the x. So our graph looks like this. And we can't see it super well because it does start up here at 24. So I'm just going to go ahead and zoom out. I think that should work. Might have zoomed out too far. Here, let's do this. Come on, calculator. Do what I want. Here we go. All right, back to standard. And I'm going to go ahead and just make these go out a little further. So I'm going to take these out to like 30. So let's make our x max 30. Let's make our y max 30. That should give us a little better picture. Okay, so there we go. So anyway, what does the y-intercept represent? Y-intercept would be your starting value, the 24,000 that it begins at. So y-intercept is the $24,000 initial price. The asymptote is your x-axis, y equals 0. So that's y equals 0. And what does that mean? Well, that means that the value approaches 0. Basically saying that eventually this car will be worth nothing. It keeps losing it's losing 20% of value every single year. So eventually it'll be worth nothing after a lot of years. But anyway, when will the value of the car be about 5,000? Probably table would be a good way to answer this question. So if I go to my table, remember we started at 24. We want to look for when this gets to be about 5. So it goes to 19, 15, 12, so on. And then it hits about 5 at 7 years. Okay, so when will be about, this will be happening at about 7 years. Which is kind of crazy. If you think about buying vehicles and keeping a car and stuff like that, you paid $24,000 for this. 7 years later, it's worth like $5,000. This is, I would say, a little high for a depreciation rate, but it's not that far off. There are a lot of vehicles that depreciate at close to this rate, and a couple years after owning them, they are not worth nearly as much. So that's a pretty good industry to make money in if you're a car salesman. All right. Next one here. Go ahead and pause for a second and see if you can answer this one. All right. So I wanted to answer the first part. This population is definitely increasing. You can see the rate here is above 1. 1.05 specifically means they're increasing by 5% per year. So anytime that B value is greater than 1, it's growth. When will the Hawks reach 280? To answer that, I'm going to go to my calculator, and I'm going to put this in. So 220, I got my equation in. Let's jump to the table. And we are looking for 280, which is right here. So this would be roughly 5 years. So in what year? So 5 years after this. So 2021, this year. Watch out on the Hawks today. All right. And that should be good for today. So we'll finish up the rest of these tomorrow.